All right. So yesterday, we started talking about ionic bonding. And we ended with our discussion on the energetics of ionic bonding. And so we discussed the type of energies that are associated with this type of bonding. I'll say it again. We had ionization energy, electron affinity, and now our third piece of the puzzle, as they call it, lattice energy. We can now get a good idea of the energetic processes that are involved in this type of formation. And when you start to understand that process, you can then build off of that to further our knowledge and further our use of these types of reactions for, really our benefit. Before we get into our next type of bonding, which is covalent bonding, I have a fun little song again. I give you these Grammy-nominated songs all the time. And so this one's about ionic bonding. So just sit back and relax for a few moments, get our brains warmed up, and then you'll enjoy this ionic bonding song.
This is the story of the alkaline metals, who were trying to get rid of even tons. All of them had one in their valence, and they wanted none. This is the story of another family. Group 17 were also known as halogens.
We call them Group 7.
7 electrons were in their valence, and they wanted 8. Till this one day when the metal met the other, the electron transferred to the halogen. Both of them got charged and were attracted. That's the way they became ionic bonds. Ionic bonds. Ionic bonds. That's the way they became ionic bonds. Ionic bonds. Ionic bonds. That's the way they became ionic bonds.
Anybody know what song that came from, or what show that came from? Oh, no one's seen the Brady Bunch? No one's seen the Brady Bunch? Oh my goodness. Classic 70s sitcom. Oh my gosh. You're Marsha? No way. Oh my gosh, I'm not that much older. Yes, I am. All right. Moving on to covalent bonding. As the word suggests, covalent, we have atoms that are going to share electrons. More importantly, they're going to share their valence in electrons. So there are several electrostatic interactions in these bonds. We have the attractions between electrons and nuclei. We have the repulsions between electrons, as well as the repulsions between the nuclei as they are bonded. This goes back to that trend in chapter 7, the bonding atomic radius, where we discussed it, where we showed that when we have two atoms coming together to form a bond, the electrons of one atom and the nuclei of another atom are attracted to each other. But as they draw closer, the electrons from both atoms are repelling each other. And at the same time, the nuclei of both atoms are trying to repel each other. So you can only get so close when you have atoms bonding, especially in covalent circumstances. So if we look at H2, H2 is the simplest example we can use because each one only has one electron and a very simple nucleus of one proton. As I said, the nuclei will repel each other, electrons will repel each other, but we have the nuclei and electrons being attracted to each other. And since this molecule is very stable, the attraction forces overcome those repulsive forces. So if we go back to chapter 6 and talk about quantum mechanical methods, we can calculate the electron density within the molecules themselves. And when we do so, we don't have to do it ourselves. The calculations show that the attraction between nuclei and electrons causes the density to concentrate between the nuclei. You have one atom here, one atom here. In between those two nuclei of the hydrogen atoms, we're going to have the density of our electrons present. And so, because of this, the resulting overall electrostatic attraction or interaction is attractive. So H2 held together because these two positive nuclei are attracted to concentrations of negative charges between them. And we can demonstrate the formation of these covalent bonds through the use of Lewis symbols. And so in Lewis symbols that we talked about briefly yesterday, we usually show each shared electron pair as a line. So if we look at H2, we have one hydrogen here, one hydrogen here. Each hydrogen has a single valence electron. These two are going to come together to form a bond, a covalent bond like this. However, in our Lewis structures and in what we will eventually see as two-dimensional line bonds in molecules, these two dots, anytime we have a sharing of electrons, we finalize our Lewis structure by replacing those two dots with a line. And these lines are what you might be more familiar with when you look at a compound on paper. It's the easiest way to draw or demonstrate who's bonded to who, what's the structure like in a two-dimensional setting. Chlorine is very similar. How many valence electrons does chlorine have? 7. So we place 7 dots around each chlorine atom. And so they just want one more electron each. And they can help each other accomplish that by sharing those two electrons. And so now they get a situation, like this, where these two are now shared. We have the other valence electrons like this. But again, these shared electrons, we have to now represent it with a line. So we'll get Cl connected to Cl and replace those dots on the outside. This is what a Lewis structure of a compound will look like. Anytime you have shared electrons, you replace with a line and place the remaining unshared electrons on an atom on the outside. So if I can find my clicker. For nonmetals, the group number is typically the number of valence electrons that those atoms will have. Like we saw with chlorine, group 7A. Fluorine, chlorine, bromine, iodine, those have 7 valence electrons. They only need 1 to form the octet, so they're going to form 1 covalent bond. Group 6 with oxygen and sulfur, you're going to form 2 because they need 2 electrons each. 5A nitrogen would form 3, 4A carbon would form 4. And so you can predict a lot of these formations simply based upon the group number that they are in. So let's try and look at our Lewis structures here. So if we look at, let's see, nitrogen and fluorine. Okay? We got nitrogen and we have fluorine. What group is nitrogen in again? Group 5. So how many valence electrons does it have? 5. Okay? And honestly, where I place those dots is somewhat arbitrary at the moment. Okay, it doesn't really matter as long as we represent them, because there's really no rhyme or reason where they need to go at the moment. Fluorine has 7. Did not mean to say that. Fluorine has 7. But how many electrons does nitrogen need again to form an octet? Needs 3. Okay? So when we have nitrogen and fluorine coming together, they have to satisfy each other. Okay? And since nitrogen needs 3 and fluorine only needs 1, we're going to have 3 fluorines join up with 1 nitrogen. And so what that looks like now is this. Nitrogen is going to be in the center and is going to be surrounded by these 3 fluorines. Okay? So now, let's put our dots in for each one. Again, nitrogen has 5. Fluorine has 7 for each of the 3. Okay? Now that we look at this, do we have any shared electrons in this image? Where, Olivia? So right here, and right here, right? And so now that we've identified which electrons are being shared, how do I finalize this? What do I use? A line. Very good. So you'll end up having a finished product that looks like this. And any remaining unshared electrons go on the outside. So that is what a Lewis structure of a compound would look like. Let's try another example. This time I'm going to do it on the whiteboard, or on my little whiteboard, so you can record it. Ow. I can't wait to not have to do this every time. Okay, so we have to compare the Lewis symbol for neon, we're right here, with the Lewis structure for methane, CH4. In what important way are the electron arrangements about neon and carbon alike? And in what important way are they different? Okay, so first thing is we've got, wrong marker. I'm just going to write these down. I'm going to write neon. What's the symbol for neon? Ne. And then we have the compound CH4. Okay. Flippy, flip, flip. All right. And lighten it up. Can you see it back there? Okay. So first, let's do the Lewis structure, if you will, for neon. How many valence electrons does neon have? In fact, what group is it in? What group number? 8. So it's got how many valence electrons? 8. 1, 2, 3, 4, 5, 6, 7, 8. All right. Next thing we need to do is we need to try to figure out what the Lewis structure is for CH4. So let's separate these out. So we know we have carbon and we've got hydrogen, right? How many valence electrons does hydrogen have again? Oh, sorry, yeah, 1. Yes, 1. How many does carbon have? What group is carbon in? 4. So it's going to have 4 valence electrons, 4 dots. So now, let's start breaking this down a little bit more. How many electrons does carbon need to have an octet? 4. Now, hydrogen is a little different in the fact that hydrogen can't form an octet. But what it can form is a maximum amount of electrons in the s orbital. Does anybody remember how many electrons can go in the s orbital? 2. Okay. So looking at the formula, if hydrogen needs 1 more and carbon needs 4 more, that's why hydrogen gets the subscript of 4. Because we're going to place 4 hydrogens around the carbon, and by doing so, we're going to satisfy each of the atoms' octet, or I guess 2-tet for hydrogen. So it's going to look like this. Place your dots around the carbon. Then you're going to place a hydrogen and its dot right next to the location of the 4 carbon electrons. And so we've got these that are sharing, those that are sharing, those that are sharing, and those that are sharing. So the Lewis structure for CH4 will be finalized with this structure. Okay? So that's what CH4 will look like. But that's not the overall question that we are to do. Yes, we had to figure out, what the Lewis structures were for each substance. But now we have to compare the neon and the carbon. So if we look at the neon, it's already got a full octet. Okay? It's not going to bond with anything. This is one of the main reasons why neon is considered a noble gas, because it is so unreactive, because it doesn't want to lose or gain any. But if we compare that to carbon, carbon in this instance does have a full octet, but it had to do so by sharing its electrons with other atoms to form compounds. Okay? So although the question may have seemed kind of like out of left field, when you really look at it, it's really just right there in front of us. These are both full in their octets, neon and carbon. But carbon had to go about it a different way. It had to go about it by sharing its electrons. Questions how to do Lewis structures? We're going to do plenty more. So don't think it's going to be the last time we're going to do it. Okay, we're going to do plenty more as the chapter goes on. And honestly, one of the last things we're going to talk about today are multiple bonds. Okay. Shared electron pairs constitute a single bond, which is a single line. However, when we have 2 electrons that are shared between a single or 2 individual atoms, then we're going to have a double bond. We can even have a triple bond. Okay? And this is, again, we'll get into these types of bonds at a later date. But one thing you want to remember is this last main statement, okay? The more bonds that you add between 2 atoms, the shorter those bonds become. Okay, so that's the general rule. The length of the bond between 2 atoms will decrease as the number of shared electrons pair increases. All right. So let's just do an example here. We've got N2. Okay. I'm using the wrong marker. We've got N2. Okay, that means we've got 2 nitrogens. And again, nitrogen has how many valence electrons? 5. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. These 2 have bonded somehow. Okay? if we just share one pair of electrons between the two, okay, if I were to cover this up, or how about I do this? I'll cover this nitrogen up. Now how many nitrogens does that nitrogen, how many electrons does that nitrogen actually have? If we count that one. 6. Does it have 8 yet? No, it doesn't. So this is where it has to start adding additional bonds between them. And so this guy and this guy, they're like, hey, we can come help too. So they come up here. And now we have a situation where we have these electrons being shared. Cover that up. Now how many electrons does that particular nitrogen have? 7. Does it have enough? Does it have its 8 yet? Not yet. So finally, we've got these electrons who can say, I can come make it work. So now then they come out here. And so now we've got this. I cover up that end, how many electrons does that one have? 8. If I cover up that electron, or that nitrogen, how many does that one have? 8. And so look how many pairs of shared electrons we have. 1, 2, 3. And now that I've satisfied the octet rule for both nitrogens, I draw my finalized Lewis structure like this. Again, putting those unshared electrons that still remain up here. This time, I now have a triple bond. So when it's necessary between two atoms to share more than one electron with each other, you're going to form multiple bonds. Now, with each bond that you add between atoms, it requires that much more energy to break them. It's like if you're going to karate chop a piece of wood. You might be able to karate chop one piece of wood relatively easy. So you add another bond, another piece of wood. Then your distance becomes shorter between the two objects holding it. Now you go try to break it. You might break it, but you're also putting in a heck of a lot more energy in order to do so. And then you add a third piece of wood. Your third bond becomes even shorter. You try to break that, it's going to take an incredible amount of energy. Have any of you ever broken sticks? I mean, I'm sure you have. Gone outside and just broken sticks? Yeah. Great. Shake your head. Shake your head. You've broken sticks. Now, have you not broken sticks before? Okay, good. I was going to say, you need to get outside. Have you ever tried to see how many sticks you can break after you've broken one? How many times you can snap it in half, put it back together, snap it in half, put it back together? Ever done that? It's harder, doesn't it? The exact same concept that's going on here. The more bonds you have, the harder it is to break. Now, when it comes to bonding, whether it's ionic or covalent, sometimes things just aren't shared equally. And that's what we're going to get into tomorrow. Okay? Called polar covalent bonds and bond polarity. Okay? So, we're going to wrap it up for today. And we will get into this content tomorrow.